Let me start it now before I forget. We're going to do it again anyway. So, okay. So the main thing with the double replacement is that they need to switch. And that one product must be insoluble. If they are not insoluble, that reaction will not take place because they'll just keep switching and switching and switching. Something has to get away from the solution in order for it not to keep switching. Okay. So right here, lead nitrate and potassium iodide will form lead 2, in this case, sorry, lead 2 nitrate and potassium iodide is going to form lead 2 iodide and potassium nitrate. And potassium nitrate is soluble, but lead 2 iodide is not. It's insoluble. Therefore, this reaction takes place. And you can predict. Now, this one, usually sodium and potassium are very soluble. So I would think that sodium iodide is soluble, and so is potassium nitrate. Therefore, no reaction. You see? So you've got to look at your solubility chart. All right, so let's go back and look at what we have here. Let's see, go back to the modules, and let me show you what I'm talking about when I'm talking about that part. Okay, come on, modules. Let's go. Right here. Oops. Nope. Come on, you. Don't do that. What in the world? That is so not what I wanted. Something happened. Hold on. No, go away. I don't want you to look at you either. All right, let's get started again because this is just crazy. I don't know where that came from. I was just scrolling down, and it just went somewhere that it shouldn't have gone. Okay, so modules, and I'm just gonna use my little, like using my finger, I'm just gonna use my scroll bar so it doesn't happen again. And it's gonna take a little longer because it's, okay, I went too far that time. Okay, let's go back up a little bit. All right, here we go. There it is. All right, so on here, let's see. Okay, it's not on here. I thought I had it on here, but it's not. So what you need to do is you need to look in your book. There is a section that'll give you both. Let me show you where the reactivity series is. Hold on, let me go back to Wiley. All right, so the activity series. Oh, you know what? All I needed was to do this again. There we go. The activity series is in this one lab, but the solubility table is not. Solubility table, I actually give it to you in the second chemistry. That's what it is. I don't give it to you in this one. Okay, hold on, solubility. All right, this is the one that I was talking about right here, this one, activity series, virtual lab. Okay, so when you go into it right here, right, you will see that there's a link that tells you to go and check if this is the right order right here, table J. That's the one right there. That is the activity series, okay? So that's how it works. Although I don't see oh, there is hydrogen. There's hydrogen. So like, where's hydrogen? But I see it now. Okay, so this is the way that you'll know whether the reaction is going to happen or not, is this one right here. Anything above will replace anything that is below. So this lithium will replace everything below it. Rubidium will not replace lithium, but it'll replace everything below that. Potassium will replace everything below it, but not rubidium or lithium, and so on and so forth. You get the gist. Same with the nonmetals. Anything on top will not replace will replace everything on the bottom, but anything on the top of the metal will not be replaced by the bottom.
Miss Venus, you can say that one more time. You kind of just one more time.
Okay, so if lithium, right, is the lonely guy, it'll replace anything that is bonded that is below it. So anything below it, like rubidium, potassium, cesium, all of them, every single one, okay? But anything above, for example, lithium, there's nothing above lithium. So we cannot talk about lithium, but rubidium, for example, will not replace lithium, but it will replace everything below it.
Right. So anything could replace lithium.
Yeah, yes. Rubidium will not replace lithium at all, ever, because it's less active. Okay, so potassium can replace cesium, barium, strontium, calcium, but not rubidium or lithium because they're above it.
And that will be the same for the non-metals for iron?
Yes.
No, that's not
yes.
iron.
Remember iron and copper? See how iron was the lonely one, right? And copper was the bonded one. If it had been the opposite, if iron had been the lonely one and iron had been the one that was in the compound, that reaction would have never happened because iron is above copper.
I kind of mixed up the element, but I was talking about the non-metal, but I got...
Yeah, it has to be the one that's alone, the one that's, not bonded, right?
Okay.
And then same thing with the non-metals. You notice that fluorine is the top, and then anything below fluorine can be replaced by fluorine, obviously, but nothing above iodine can be replaced by iodine, for example. Okay. Make sense? Okay.
It does. Thank you so much.
You're welcome. And like I said, there is a solubility rules. If you look it up, I thought I had them on there, but I don't see them. But in your book, I do believe they're in there. So that's what I was going to show you. I was going to find it in your book. So I'll just go back to home, I guess, to show you where the solubility rules are in your book. Okay, so go to the book first of all, right there. And we're going to look for solubility rules once we get to it, because it is searchable, I believe. Nope, it is not searchable. At least I don't see where I can search. Okay. Nope, but we're going to look it up. Let's see, table of contents. All right, now I can see it. All right, let's see, introduction. Nope, nothing here so far. Composition of substances in solutions. There we go. Stoichiometry. Yeah, that's got to be it. That's got to be the one, chapter 3. So let's just go there just to see. Well, let me see. Chemical nomenclature, key terms. Yeah, no, that's not going to be it. It's going to be here somewhere. Solutions. Come on. Why is it not going there? I clicked on it. Oh, there it goes. Finally. It took forever. Okay, so here, if you find it, you will probably see the solubility rules in here. Determining empirical and molecular formula. Other units for solution concentration. Nope, it's not on there. I don't see it on there. I can't. Oh, there we go. You search it. There, yeah, you can search it. Okay, good. That's what you want. You want to look for solubility rules. There we go. Uh-oh, there's been a glitch. Why did I not spell it right? Solubility. No, I did spell it right. Maybe I'm just searching the wrong chapter. Okay. Why are you not letting me see it? Update. Okay, so it's not doing it. Why is it not doing it? Well, you know what? There are other books, other solubility rules that aren't there. So we'll just look for them somewhere else, which is what I usually do anyway. Solubility rules. And I'll tell you the ones that I like. Chemistry Libre. See, there they are. They do exist. Okay, solubility rules. There we go. And that is the same kind of book. See, there it is right there. There's all those 11 solubility rules. You notice it says salts containing group 1 elements are soluble. There are a few exceptions, and it tells you ammonium ions are also soluble. Okay, and then it says salts containing nitrate are generally soluble. Salts containing chlorine, bromine, blah, blah, blah. See, those are all the solubility rules. Okay. So you can take a picture of it if you want. But there they are. There's all the solubility rules. There's quite a few. So you can't try to memorize those. I wouldn't. I like, there's another one that's a little bit better than that one though. Let me see if I see it. I don't like those. No, no, don't like you. No. Kim Tonk, no. I am trying to find the ones that I like, but I don't see them. Is that the one? No. Yeah, there's the one with the exceptions. Let me see if that's the right one. No. The one that I like is it's actually very generalized, and it'll tell you what's going to happen, like strontium and something else do not make soluble, like that. And it is I'll post it if I have it in my other class, in the one that I told you about, section 2, I have it in that one. So the one you're taking next. Anyway, so let's just look at the next part that we're going to look at, which is how do you determine which kind of reaction do you have? Okay, so let's look at this practice sheet, and we're going to look at 2 or 3 different things on it that are important for us to know. So what would you say? A chemical reaction is a process in which what? A, B, C, or D? Which one would you? Just put it on the chat, A, B, C, or D. Okay. Anybody? Nobody's answered. All right, so in this case,
A chemical reaction.
yeah, a chemical reaction is what?
The law of conservation of mass applies.
For sure. What else? Anything else? Can you see?
Is it D?
Yes, it is.
Yeah.
All of them. Yes, correct. Okay, the next one. During a chemical reaction, what happens? And you got to be careful with these semantics, because that's exactly what this is about.
The atoms are rearranged.
Yes,
D?
that's the only one. The other things, nothing's get reproduced or destroyed, remember? All right, what about 3? How do you balance an equation? There's only one way.
Coefficients.
Uh-huh.
Adding coefficients.
Coefficients, right, correct. And the other one, an atom's ability to undergo chemical reactions is determined by what?
The outermost electrons.
Correct. That, because the middle ones do not matter. All right, next one. What are the reactants in the following equation? So basically, this is just a thing of knowing, you know, which one's which. So what are they?
Zinc and copper 2 sulfate.
That is correct. And what are the products?
The product is zinc sulfate and copper.
Correct. All right, so see, not so bad, right? So this is just, like I said, a preliminary thing just to know that we know what we're doing. And now we have to classify them. Okay, so let's look at them carefully and see what's going on. So you see how there's a lonely metal and there's a lonely element in the other side, right? So that means this is a what? What type of reaction is this?
It was just in my head and it come up.
Okay, that's fine. I'm just going to put initials once you say the answer. This is a nope. Don't know yet? You'll know soon. Once I say it, you'll know. It is a single replacement because only one thing is replaced. You see that?
Right. Yeah.
And based on the table J that we were looking at, right? It will happen because zinc is above hydrogen. Or is it? See, some of these we just say they'll happen, but will they really? Let's look. Let's look based on table J. Didn't I put it on here? There it is. All right. Is hydrogen below zinc? Yes, it is. See? So that will happen. So that is a correct reaction. Pretty good. Oh, wrong one. Sorry. There we go. All right. So the next one, what's going on? What do you see happening? What do you see happening here?
The cup. I'm seeing that one of the oxygen was added to hydrogen, so it
No.
becomes water.
Okay. Yeah, but there's the key that you really should be looking at. How many reactants do you have?
2.
No, reactants.
Oh, hold on.
That's the thing on the left.
Right.
How many do you have? Only one, right?
Only one, yeah.
And how many products do you have?
2.
So this means it broke up, right? So
You're
this
right.
is a decomposition reaction. You see how it broke up into 2 things? We're going to go back and balance in a minute, but first we're just classifying. All right, what is the next one? Okay, look at it. What's happening? Okay, usually when
The what you call it? It switched. Not switched.
the positive, the positive ions have switched partners, correct? Which is known as a double replacement. Okay, see how that works? completely replaced. What about the next one down? What's going on with that one?
Would this be a single replacement?
Single replacement, correct. Because you have one element completely being replaced by another with no joining of anything else. It's just completely being booted out, basically. All right, number 11. So what does that one show you? This one's this is where you got to remember the things that we learned when we were looking at the PowerPoint. There's those
Decomposition, because it lost.
This is not a decomposition.
No?
No, because we have two things on the right, on the left.
Okay.
So it didn't break up. It is doing something else.
I know it lost.
Remember what something that doesn't happen unless oxygen is present? What is that?
No, hold on.
Combustion. That's right.
It was correct? Okay.
Combustion. Yes, it doesn't happen because if you don't have oxygen, nothing can burn. And see, all this is propane gas burning in oxygen, producing carbon dioxide and water. And the last one, what do you think it is? Look at the same product, same everything, right? So combustion, and that is alcohol. That is ethyl alcohol burning in oxygen. So, okay, so now let's balance. Let's see, are we balanced? Let's see, one sulfate. Yeah, this one's balanced, so check. This next one, no, this one, 3 carbons, 2, yep, that one's balanced. That is balanced, 3 oxygens, 1 carbon, yep. Next one after that is not balanced because we have 2 chlorines and we need 2 of those. Therefore, now it's balanced. See how easy that one was? Next one after that, nitrates, there's 2, so we need 2 of these right here, right? And we need 2 silvers now, and that's balanced too. Okay, these are a little harder to balance. Remember the tip I gave you, always look at your hydrogen and divide it by 2. If it's an even number, then you don't have to double. So you don't have to double. So you put a 3 here because there are 3 carbons, and you put a 4 here because there's 8 oxygens. Okay, so now 3 times 2 is 6 plus 4 is 10 divided by 2 is 5. So 5 there. See how I do that? Okay, so basically I multiply these 2, right? 3 times 2, that gives me 6 for this side. And I can write it down, I guess. Let me see about writing that down. Okay, so that's 6 on this side. And then 4 times 1 is 4. So, oops, see, this is what I don't like. This is why I was trying to avoid that. Because it is, for some reason, it is doing this crazy thing. I have to actually make sure I put my finger down. There we go. That equals to 10, right? 10 divided by 2, which is this 2, is 5. See? That's how I do that. It makes it faster and more efficient to do that. All right, clear that. Okay, now the next one. This one's a little more complicated because we do have an oxygen that is sticking to the hydrocarbon. So you actually have an odd number here as well as on the products as well as you have on the reactants. Therefore, you just got to balance. All right, so you've got 2 carbons here. You only have 1 there, so let's put a 2 there. And we have 5 plus 1, so that's 6 hydrogens on this side, so we need a 3 there. Now let's see how many oxygens we have. Okay, so oxygens we just made. Let's see, let me tab it over there on top. So maybe I can write it like that. 2 times 2 is 4. And then we have plus, right? 3, right? That gives us 7 total. Okay, but since we have 1 that's lonely over here, we subtract that from the 7 that we have. So we say 7 minus 1. So to do this correctly, we would say 7 minus 1 gives me a total of 6. Now 6 divided by 2 is 3. So we've got a balanced reaction now. You see that? So that's how I do math when I do the actual oxygens with these, because there are some numbers on here sometimes, some big numbers. So, okay, so now what we need to do is write down exactly what it's telling us to do. You notice it says is the product. So that means that magnesium chloride is not going to be, it says is the product of magnesium and chlorine. And remember, chlorine is diatomic. Oops, that's an Mg lowercase. Sorry. And this is diatomic, so we need a double. And we are saying it's the product, which means that goes on the left-hand side. The magnesium chloride goes on the right. So MgCl2, based on what we've learned how to do. Now we need to balance. Actually, there is no need to balance. They're already balanced, right? And that's that. Now, what kind of reaction is this? What's going on? You have magnesium and chlorine becoming magnesium chloride. So there's only one product. One product means synthesis, right? See, you can tell because things are being put together. And that's what synthesis means, is to put together. All right, and then the next one is copper 2 hydroxide and potassium sulfate are produced when potassium hydroxide, so KOH, reacts with copper 2 sulfate, oops, sorry, plus copper 2 sulfate, so CuSO4. Okay, so that's what it's telling me to do. Now we're reacting. That means we're producing copper 2 hydroxide, so CuOH2 plus potassium sulfate, K2SO4. Okay, now let's go and put the 2's where they belong and the 4's where they belong, because they all belong, and it's a subscript. All right, now, do we need to balance? Yeah, we do, because there's not enough potassium to go around. Now there is. We have 2 potassiums and 2 hydroxides. So there you go. It's balanced. And what kind of reaction is that? This reaction is a double, right? Replacement, where potassium and copper switch places, switch partners. All right, and that's how you do those. Now, if we wanted to do more practice, we can go back, which I do want you to do more practice. So we're going to not save that. And we're going to go back to the sheet that we did earlier, all those sheets that we did earlier, where we have reactions on them. And once you do that, you'll be very, very sure of what you're doing. Okay, where are your reactions? Not there, not there. There, that's what I need. All right, so the balancing equations. Okay, we're going to do this one. I'm going to download both of these. I'm going to do that one, and we're going to do the other one too. And we're going to do, where are you? No, that's not it. Oh, stop it. Why do you keep doing that to me? Okay, there we go. And we're going to do this one. Nope, not you. You. This one, balancing equations practice. Okay, so we're going to do both of those. We're just going to classify them. We already did the balancing, right? So we're just going to classify them now. Just going to go look at them and see if we can tell. All right, so let's look and see what's going on. Remember, we have little tips on how to tell what's what. All right, so when you're looking at something alone, replacing something, that's a single replacement. I'm going to put it on the first, on the beginning here, SR, right? Single replacement. All right, this next one is a double replacement. You can see because you've got hydrogen and sodium switching places. You see that? Okay, this is a decomposition because it's breaking up. You see how it works? It's breaking up because you have only one. Oh, come on, give me that. Okay, only one right here, only one reactant becoming two products. And that right there always tells you that's a decomposition. This one having oxygen on the reactants and carbon dioxide and water in the products tells you immediately this is a combustion. Same here for number 5, same thing is going on. Doesn't matter what it is. You can see that it's a hydrocarbon. Okay, this one is a synthesis because it's exactly the opposite. You have two reactants being put together into one single product. You see that? So you know it's a synthesis. In this last one, very obviously it's a double replacement, right? Because you have the silver here moving where the sodium was and the sodium moving where the silver was. As a matter of fact, let's make these different colors so we can see. We can actually see the movement. See how the sodium is now over here with the NO3 and the silver, which should be yellow, is over here with the chlorine. Oops, nope, chlorine. Thank you. There you go. See, you can see the partner switched. All right. All right. So that's that one. Let's go to the next one. Don't save that. All right. Let's look at the next practice that we have. All right. This one. Someday it'll open. There we go. All right. So I'll let you guys tell me what you think number 1 is. What do you think it is? What do you think number 1 is? What's going on? Pay attention to reactants and products and tell me what's going on. Okay. How many products do we have? 1, right? But we have more than 1 reactant. Therefore, this is a synthesis. It's being put, oops, undo that. Sorry, I didn't mean to close it off. I just meant to put an S. All right, so that's a synthesis, see? The next one right there, KClO3 becoming KCl and O2. Just look at what's there. That is a decomposition because you have only 1 reactant. You see that? That's how you know. In this one, well, you have 2 things that are lonely, and they're the different things. Therefore, this is a single replacement. because one of them booted out the other one. And would this have officially happened? Yes, because fluorine is more electronegative, right? So it's stronger than chloride. All right, than chlorine, sorry. Silver nitrate, magnesium chloride, becoming silver chloride and magnesium nitrate, double replacement. Both of them switched places. Look at the next one. What do you think that one is? You got that is another double replacement.
Single. Oh,
right?
double because they have two products.
Yes, and
Okay.
also you've got, okay, so if I color them, like I give aluminum yellow and I give bromine, let's say green, you'll see what happens. That's when it really becomes quite obvious. Let's give potassium blue and potassium blue, I said, okay. And let's give bromine the green, right? And let's do sulfate in pink. You can kind of see it more if it's colored. It's actually very obvious when you see it like that. See? See how the two colors switched? The green, which was with the blue before, with the yellow before, is now with the blue. And the pink, which was with the yellow before, is now with the, the blue before is now with the yellow. So they both switched. These two switched. So that's why you can tell. Okay, what about the next one? Remember, there's a thing that always tells you what it is. There's the products, the reactants, and looking at all of that. You got to look closely. Right.
Combustion.
That is correct. And because there's oxygen, right? And the products are carbon dioxide and water. Now, there are some times that you will have carbon dioxide and water as the products, but if there's no oxygen on the reactants, then it's not a combustion. This one can be two things, right? Because it can be a combustion because it meets both of them, but it can also be a synthesis. You see that? Wouldn't you say? Because it meets the fact that you have oxygen and that the products have oxygen. So that's part of it. And it also meets the fact that you had only one reactant. Well, only one product and two reactants. So what about the next one? What do you see happening?
Synthesis, because it's one.
The opposite.
The
Reaction of synthesis is decomposition, because the product is the one that is double.
That one. I thought you were talking. The one before was a synthesis.
Yeah, the first one's a synthesis. Yeah, 7.
That's what I thought you was talking about. P plus.
Yeah,
that one.
that one's a synthesis, but the next one's a decomposition because it's exactly the opposite. You see how this one is only one product, but here there's only one reactant. So that's where you have to focus on. And the last one, what do you think it is? Usually those are the ones people can tell very
double
quickly
replacement.
what they are. Yeah, exactly. See, it's not so hard once you get used to seeing them, right? It's those
agreed.
Those little clues that you got to look for. Yep. And you notice that I said that first one could also be combustion, that number 7, because of the fact that you have oxygen, which was part of the the clues that we had, that it had to have oxygen in the reactants and contain oxygen in the products. And it does both. Just like if we had magnesium, let's say we had this other reaction right here, and it was, you know, this is, I don't know if you've ever seen it, but when magnesium burns in oxygen, right, it produces magnesium oxide. And that can be both a synthesis and a combustion, because you're making a new product, but you're also burning it. And that is exactly what happens when you do the magnesium ribbon burning. I don't know if you've ever seen it. It's a cool reaction. You can really see what's happening when you see this reaction in action, which is what we did earlier on this, let's see, on this sheet. Where's that sheet? Where did it go? Is it this one? No. I don't know where it went. I had it up there, but I don't see it anymore. Anyway, but that's it. That's the way to tell. Like right here, this one right here. This is what I was talking about. We didn't save it, but that magnesium and oxygen reactions right here. Except it's magnesium and chlorine, which is the same thing. Except it cannot be, right? Oops, that's a plus. No plus there. That cannot be a combustion because there's no oxygen. See? That can only be a synthesis. There's the difference between those two. Okay. All righty. That's basically it. Oh, Jean Marie, I had Dr. Gorski go get a few materials for me, and she's going to have them in the lab. So if you get a group together and do that experiment, you can get your bonus points.
Okay, thank you.
I don't know if she has done it yet. That's why I haven't put the announcement forth yet, because she's gonna, she's gonna let me know when she's got them and where she's got them. And I think we have enough 100 milliliter beakers that you don't even need to buy any materials at all.
Okay, thank you so much.
No problem. So everything should be in the lab at least by next week, if it's not already.
All right. Thank you.
You're welcome. All right. So any questions, anybody? No? We're good? Can do more practice if you need to. But if you don't, that's fine. We're done. All righty. See you Monday. Bye.
See you Monday. Bye.
Bye-bye.